Hello everyone, and welcome to video 1 of this tutorial series on the Robot Operating System 2. This video is going to be an introduction to what ROS2 offers and what it is, and we'll get into how you can actually use it on your computer. If you're watching this video, you're probably looking to work on robotic software development. Maybe you're looking to get into the industry as a software developer, or you're looking to get into academic research and work on robotics in a research setting. That being said, if you just happen to stumble upon this video and this caught your attention, regardless, we're still going to give an introduction to what ROS2 is and what programming robots looks like, so that maybe if you're brand new to this, you can at least get a lay of the land and see if this is something that you're interested in learning. And if you kind of like already are in getting into the field and you know that ROS2 is something you want to learn, at least you can get a high level overview of what it is so you can understand it. And in the next few videos in this video series, we'll cover how to actually work with it on your computer. So before getting into robotics programming and like the nitty gritty of what's going on under the hood in ROS2, let's talk about what it's for. So ROS2 is all about getting your robot working fast, and we'll get into what programming robots looks like, but it's a pretty complex task. It's different from programming other common software systems, and there's a lot of different tools and software packages involved. It's a whole tech stack in a manner of speaking that you would want to learn. And ROS is really one of the main enablers of people to use these different tech stacks, people to use simulators to simulate, environments with physics and test their robot before they actually create anything in terms of hardware, before they create parts and put together a robot and, potentially test it with faulty algorithms out in the field. They can test it in a physical simulator with tools like Gazebo. You can visualize if you're going to implement some kind of sensor on your robot, like a camera or a LiDAR, you could visualize the output of what that sensor would give you in the real world with, again, the simulator. Or you can just view live what your robot is viewing in a real physical environment using these tools. And I'm not saying that this all falls under the umbrella of ROS. These are independent tools. They just work seamlessly with the robot operating system so that you can start to pick it together your full robot from the component level. What sensors are you using? What sort of computer architecture you want to work with, and actually testing it out in the field based on your robot model. That is all stuff that you can do with ROS, and you don't have to do it from the ground up. Imagine needing to implement all of these different packages yourself. Imagine needing to create a simulator from the ground up, not being able to share with other people's work. Imagine even just modeling your robot itself. How did the wheels work in terms of a software program? What does that look like? How would a LiDAR work in a simulator? What does that look like? If you had to program that from the ground up, that would take a long time. Whereas with something like ROS, you can just take a package and get started using it. And you can really focus on the sort of problems that you're trying to solve with robots, rather than focusing on every little detail going on under the hood. So in today's tutorial, we're going to be covering the unique challenges for writing code for robots and where ROS2 comes into the picture to solve some of these problems, the core concepts that you should know to use ROS2, the internal architecture, what's going on under the hood that makes ROS2 work, and finally, normally with a tutorial on ROS, there's a pretty lengthy procedure that would have to be followed to install it and get it running on a computer that you might have. What makes it long is that this isn't just a software package that you download off the internet and it works like you just open an executable file like usual and just go through a few buttons and then it works seamlessly on your computer. ROS2s typically run on Linux systems. So before we even installed it, normally the process would be if you're probably watching this video on a Windows computer or a Mac, you'd likely have to install either a virtual machine or dual boot your computer. install the correct distribution of Linux for the ROS2 version that you're trying to use. And then you'd have to go into that Linux system that's dual booted or on a virtual machine, go through the process of changing some permissions so that you can actually install the correct prerequisites and for your Linux system to actually enable you to do that. Then you would have to install some prerequisites, and then you can install ROS2, and you would verify each of those steps. So that would, when I've taught workshops on ROS2 in the past, that's been the most lengthy item. And I don't want you to need to do all of that because that can be frustrating and some people can get stuck there and never actually get to working on their robots and making them do cool things. So in order to just have the easiest introduction as possible to ROS2 and just get started understanding how to use ROS2, we're going to be using a web simulator instead to get started. And when it comes to programming robots, in order to talk about ROS2, we should understand what is the unique challenge posed by programming robots as opposed to other software systems. So really what makes robots unique is this sense, plan, act architecture, where the sense, plan, and act portions of it are really what's running on your computer. But you also have some new peripherals, like with your laptop or desktop that you're watching this video on, you might have peripherals like your mouse, like the microphone that I'm speaking into. You might have different items that are connected to your computer. And with robots, there's some unique peripherals, sensors, actuators that do different things. Sensors sense what's going on out in the environment. You might have a camera that's checking, images or video of the environment and acting as the eyes of the robot. And that's a sort of sensory information. You might have a microphone. The robot is hearing what you're saying to it, so it can interpret that and perform some sort of action based on what you're asking for. And you also have actuators, another sort of peripheral where it's actually enabling the robot as opposed to a regular computer. Your desktop's just kind of sitting in a location, it's doing purely software work. A robot has actuators so it can actually navigate in its environment, interact with its environment. You might have motors that move this computer that forms the brain of the robot around so that it can do its tasks. You might have um, a robot arm that can pick up something, and the grasper and the motors inside of that robot arm would be a form of actuator, so it can actually accomplish its task of using that arm to perform some sort of work. And finally, an interesting example, you might have a speaker as an actuator. So a lot of people use actuators in terms of, linear or rotary movement, but really actuators are, you could think of them as anything that actually impacts your environment or produces some sort of new effect within your environment that the robot can perform work with. And if the robot were, for example, physically speaking to you, so you speak to it and it speaks back to you, a speaker would be an example of an actuator because it's using that to produce the sound that you're hearing. And with those two categories of peripherals, under the hood of the computer, you're going to be running software that lets robots form a sort of artificial intelligence. When we talk about artificial intelligence in this sense, it's not necessarily machine learning, neural networks. We just mean artificial intelligence in the broad sense of um, you are imitating what a human would do on a computer. And the cycle of work going through a robot is it's picking up some kind of sensory information. And then from that sensory information, it's creating a plan for how to act. And then using the actuators, it's actually acting on that plan and performing some work in the real world. Um, that is what makes a robot as opposed to a machine. A lot of people say robots are being used for repetitive, monotonous, mundane tasks, and that's true. But what makes a robot as opposed to a machine is that it actually comes up with its own plan for what to do in response to sensory information, and then it acts on that plan. It's not just pre-programmed, hard-coded to do the same, set of movements again and again, but it's actually detecting what's going on in its environment and responding to that stimulus. So If you're interested in programming robots, some skills that you would want to know are on the slide. You do not need to know anything except for some introductory Python as a programming language. Python is what we're going to be using for all of this tutorial series. In order to participate with this tutorial series, we don't expect you to know any of this other stuff. You'll pick up some of these skills along the way, and you can always go back and dive deeper into them. But knowing these ahead of time, if you know them from another context, would greatly benefit you. Um, because not only are you gonna better understand what are we showing and how you can make changes to that given your background in order to produce a new effect, but also these are the skills that you would need to actually work in the industry. Uh, so we're going to be using Python, but C++ is heavily used in robotics as well. These are kind of the two main languages. Typically, what that looks like is Python is used for prototyping, for showing a proof of concept, and then C++ is used for production systems when you want something to perform quickly, efficiently. C++ is much better at that. It's from some benchmarks, typically can move 3 times or more faster than Python across your algorithms. You would want to be familiar with an IDE. We're going to be using Microsoft Visual Studio Code. In our simulator, there's other options, of course. You don't necessarily need to use VS Code, but that's what we're going to be using here. And you would want to be familiar with IDEs generally. You would want to be familiar with Gits and Docker, really version control, deployment systems, continuous integration and development. These concepts that come from regular software engineering and software development are still going to be present within robotics. And again, you don't need to know really anything about these to participate in this video series, but it is something that you would want to pick up if you want to work on robots. Um, One of the ones some people don't like to hear, you should know math. You don't have to be the greatest mathematician ever, but knowing mathematics is going to help you understand a lot of the different software that you can work on within robots. And really, the main math that you want to focus on is linear algebra, Bayesian statistics, and which is like probability math and um, calculus. And again, this isn't going to be like every 2 seconds we're solving a math problem. That's not how robotics works. But in order to understand a lot of the different systems that are being deployed on robots, there is a need for a math background. And you will eventually run into a problem in robotics where you're solving it with math. You would want to understand the hardware itself, working with computers. Um, I show an example of an Arduino Uno and a Raspberry Pi because these are two common hobbyist platforms, and they're used pretty heavily in like probably your first robots, or if you buy a kit, they might run on these systems. There's other, of course, microcontrollers and embedded computers that you can use, not just on the hobby side, but um, on the industry side and academic research. These aren't going to be the only tools you use, but this is a good sort of starter platform if you're not familiar with that skill set in terms of programming low-level hardware, programming motors to move, connecting with a network over like an edge computer. These are probably two good devices to pick up and start to get familiar with. And once again, you don't need to know these. I will give some interesting facts about how the simulator that we're using is going to be reflecting the performance of a Raspberry Pi 4. So what you can run on the simulator, you can run on one of these little cheap computers, and that you can deploy a real robot with that computer. So it's a skill that's worth picking up. And finally, um, while you can install ROS2 on Windows and Mac distributions, Linux is kind of really the core of ROS2. It's going to be what you're using across robotics development in general. So that is, again, you don't really need to know any of Linux to follow along with what we're going to be doing throughout this tutorial series, but it's going to be one of those valuable skills where as you learn more about Linux, you're going to understand what we're doing a lot better. And that way you're not just following along and playing in like the sandbox, but you're starting to think more like a developer, like an engineer, and saying, what are the changes that I can make to what you're seeing on this tutorial series? Now, we talked about how the software in a robot is different from other software systems, and looking at it a little deeper under the hood, you can see kind of some of the modules that you would expect in like classical robot software architecture. For example, you'd have a low level and high level code. And when I say low level, I don't mean to say it's more basic than the high level code. I mean to say it's closer to the hardware. So this is the code that's moving signals on circuits, controlling peripheral devices like motors, stuff like that. Detecting where the robot is just purely from sensors and just getting that sensory data. That low level code can look like a lot of things in robotics. Here's some examples are motor control, odometry calculations, but there's definitely a lot more. And you would also have high level code, where high level means it's a little further from the hardware. You're not looking at it on such a like under the hood level. You're abstracting out a lot of concepts. If you're coming from a computer science background, that might make a little more sense to you. If you're struggling to follow along because you feel like you're being bombarded with new concepts, don't worry about trying to understand every little detail that's going on here. You don't need to know everything as a prerequisite in order to move on to the next step. Especially once we get hands-on with the robots, a lot of these concepts might get a little more clear. But just understanding on a high level, what are we talking about, will definitely benefit you in knowing and understanding what we're showing afterwards. But high level code, you might have your robot actually coming up with those plans that we talked about, actually creating maps of its environment so it understands the information that it's working with, the information coming in from sensors. And the application level on the top is what you and I are seeing when we interact with a robot. When we come in as developers and work on robots, we're more than likely interacting with a user interface. If we're operating a robot out in the field instead of developing for a robot, we'd also interact with a user interface to, communicate what we want for the robot to do, um, get it started. That would be an avenue. And, all these different software packages that we're going to interact with to use ROS2 are going to be on this application level. You can imagine that, each one of these individual modules, not just application level, high level, and low level, but getting more into the nitty-gritty of a robot, knowing how a user interface works and how to program one, knowing how path planning works and how to program that, knowing how localization and mapping works and how to program that. These are all individual tasks and skill sets. And it can be difficult to go through the process of learning all of those and implementing them from the ground up. So really, that poses a difficult challenge for the field of robotics and brings about the need for the robot operating system, which we'll talk about it more, but it's not an operating system. It's just a helpful name to understand, but it's really more of a middleware to accomplish this task of tying together all of these modules and giving you a platform so that if you want to focus on just one thing, like I want to learn the user interface and how to make a nice, great user interface for robotics, but I don't understand as well to the same level of expertise the path planning and localization and mapping and motor control aspect of robotics. Using ROS2 will give you a head start. You can get started working on your portion, your contribution, and tie in some of these other modules in a way that's standardized, in the way that the communication between these modules is also standardized. So not just the modules, but also the communication between them. And that way you don't have to program everything about your robot from scratch. There's benefits to doing it from scratch. There are a lot of different companies out in the industry that build their own proprietary software architecture for their robot. But ROS2 is widely used in the industry for people who don't need that as a value proposition. And for a lot of open source developers, researchers, because it's solving a lot of problems that roboticists were facing. The lack of standardization between, communicating between these different modules and also the programming these modules itself meant that sharing code between organizations was difficult. Imagine you're an organization that focuses on, um, let's say, self-driving cars, and you're really good at motor control and fine tuning the car's path. And then here comes another organization that is really good at creating a map of the environment and working with GPS and LiDAR and camera, computer vision. And they can give information to your motor control algorithms in order to better drive your car, in reaction to the environment. So now you have context for what's going on in the environment. You're making more of a robotic system and it's planning and it's acting on it. And now both of these organizations want to work together, but imagine you both created your programs from scratch, from the ground up, in-house. And now that you're kind of coming together, there's going to be a very lengthy process of understanding what did the other person work on? How did they build their software from the ground up? And how do we need to rewrite some aspects of our software in order to integrate it with their module? That's a very lengthy process. That can take a lot of time. It's going to slow down the progress that your organization can make in contributing to your solving your problem with your robot. And so by using something like ROS2 that standardizes this communication methodology and also how modules are implemented, you can reuse code from other organizations. So not just bringing together companies or research labs, but also open source developers will put things out that different groups working on robots can use and just grab some code that works and put it immediately into their robot and solve a problem without needing to do everything from the ground up. You will also be able to make more complex robots because rather than focusing a lot more on those lower level details and how do we actually tie all the system together, you have this modular simplified architecture and you can start to focus on solving some of these bigger challenges in robotics. And you can rapid prototype across those challenges. You can quickly iterate. You can say, I have this idea for a robot, and it's not recreating the wheel every time you want to implement an idea. Now you're really just focusing on the finer details of the idea that you're trying to put out into the world. And finally, by having this standardized system that's widely used and allows you to reuse code, we're promoting engagement with the community. More people are coming into robotics from other backgrounds. Maybe you're coming in from a background of networking, like network architecture as a network engineer. Maybe you're coming in from machine learning and you want to implement vision systems or natural language processing so the robot can see and speak. And this way, you don't have to learn every single detail about robotics from the ground up in order to start to work on robots. Once again, you can focus on what your contributions would be, what you want to work on, and abstract out a lot of this other stuff that you would need for a robot. You could understand it on a high level, but you don't need to start from scratch every single time. ROS is developed by the Open Source Robotics Foundation. Just like other software systems, just like operating systems, like, with Windows, you might have XP, Vista, 7, 8, all the way to 11 that we're using now, different versions of Windows. For Linux, you'd have different distributions, like we're going to be using Ubuntu, but there's Kali Linux, there's other distributions. So with ROS, there's different distributions. There's always a long-term support distribution, which means that it's the current public, well vetted. They strongly believe that everything works. It's not as prone to going down. There's not as many beta features that could change how something happens or, um, crash your systems. So really, for the sake of this tutorial series, we're going to be focusing on the long-term distribution system of ROS. The current one is Humble, ROS Humble. But that may change if you're watching this video in the future. The typically as a developer, you're going to want to use the long-term support distribution unless you're a beta tester, alpha tester, you're looking at some new features that may be coming out in the future that you want to try on your robot, then you may consider one of these other distributions. But for the sake of this tutorial series, we're going to be using Humble. Now, Um, when it comes to ROS as a software architecture, everything that we interact with is going to be in the application layer of ROS. So any files that we interact with, anything that we install and touch on, any code that we write ourselves or that we grab from somewhere else is going to go into this application layer. It's what we interact with. But there's other aspects of ROS that are going on underneath the hood. The client layer is going to depend on your programming language of choice for developing your systems in ROS. Again, two common ones are C++ and Python. There's other options. You can develop in C and C Sharp and Java and Rust. The most common two are going to be C++ and Python. And each programming language would have its own API so that it can take your high level abstracted out scripts for ROS developments and convert that into something that's usable by your hardware from your programming language to the hardware. So that's in the client layer. The middleware layer is really one of those fundamental aspects of ROS2, and we're going to understand what that does. Uh, as a default, um, ROS uses FastDDS. You might use other sorts of middleware packages if you're working on production systems at different organizations that have other needs, like maybe there's a need for higher security. But for the most part, we're going to be focusing on FastDDS. We'll talk a little bit more about what that is, but it really manages communication between your different modules that you're creating in ROS, both for low-level code, high-level code, application-level code. Um, this is going to be your methodology for communicating between all of these different packages. And finally, you'd have an operating system layer. Like I mentioned, Linux is really going to be what we're using. There are ROS distributions that work with Windows, with Mac, but they're not as supported. And most software that you write for robotics is going to be written for Linux on Linux. If you put a robot out into the world, probably the embedded computer that you're running on that robot is going to be housing a Linux distribution. So, um, for the sake of this tutorial series, we're really gonna just be using RCLPy because we're using Python, FastDDS because we're using the default middleware layer, and Linux. And once again, you're not going to have to install Linux. You can use it on your native Windows or Mac computer through the simulator that we're going to show. Now, DDS is kind of important to understand if you want to know what ROS2 offers, because a data distribution service is really going to be that methodology to communicate between nodes. Other communication protocols have been used in ROS in the past. If you're coming from a computer science, engineering background, this may make a little bit more sense to you. If not, and you don't know what I'm talking about, don't worry too much about understanding every little detail. Just focus on the high level of what problems this solves. But in the past, UDP, TCP have been used, and ROS moved to DDS mainly to establish some of the important features that we're going to see that are part of the ROS architecture and ecosystem. The publisher subscriber model used in DDS is a fundamental part of ROS. Data can be organized and understood around topics, so it provides a layer of abstraction that isn't available in UDP CCP that's transferring raw data. And on the topic of transferring raw data, DDS allows you to exchange data as objects rather than just raw messages. If you're coming from a computer science background, that may make a little bit more sense to you. But that's an important feature because there's a lot of context and formatting that can be captured by sending something as an object type rather than just raw data in primitives. Finally, DDS provides some important quality of service features so you can control aspects like latency and the reliability of your system. And you can actually scale your system out to not just a more complex robot, but also more complex robotic systems. So you might have a distributed system. You might have a robot that's operating with a ground station and a teleoperation station. And this robot system starts to become more complex. Or you might have a multi-robot system. Like if you've seen those drone light shows, they're pretty cool, where you have hundreds of drones forming an image in the sky with different LEDs. Imagine trying to get all of those robots to work together. That's a difficult challenge. But DDS really enables the scalability of different systems. So you can write software that works across, you know, systems as they become more and more complex, and you can still maintain a level of a performance. Now, getting into what's underneath the hood of the robot operating system, you're going to have um, this publisher subscriber model as kind of the most fundamental aspect of ROS. And in this image, what you would want to understand, we can understand it with an example. So let's say you have a camera again on your self-driving car, and that camera is taking images, taking video of the environment of the self-driving car. So you would have a node called a publisher where that publisher is grabbing that sensory information and putting it out so the rest of your robot can see it. So other parts of your robot can actually use that data from the camera. And then, we'll get into how that's formatted when we get hands-on with ROS. But that allows you to also have subscriber nodes. And subscriber nodes could be like if you have a model that runs, you have a machine learning model that runs and looks at that image data, and then it detects whether there's certain objects in it. Like maybe your self-driving car is looking at a traffic light and it wants to see what color is the traffic light. Is it green? Is it red? Do I go or do I stop? And so that would be a part of your software system. That would be a module that's interested in that image data that's coming from the publisher. And similarly, what if you have a teleoperation station? You have a ground station, you have a user with a user interface who's looking at what is the robot looking at? And they want to see like live streaming, show me what the robot is seeing in the road. That is also something that would want that image data that's coming from the publisher. So that would be another subscriber. And you could start to see how, as you have different software modules that are running on your robot that can use that data, you can start having many subscribers. So you can have all of these subscribers looking at what raw data is coming from this camera and then doing their own work. Now, ROS builds upon that publisher subscriber model with this client server model of communication, where, with the publisher subscriber model, every time the camera gets an image, every time the camera gets some video feed, it's just streaming that to all of its subscribers. So all of its subscribers are continuously receiving that information. But sometimes you don't need a continuous stream of information. You need different software modules to request for another software module to do something and potentially get a response. So let's say, going back to that same example of the self-driving car with the camera streaming, publishing camera data to all of these different subscribers, you have a subscriber, again, with a machine learning model. It's looking at a traffic light and it's detecting whether it's green or red. And let's say your self-driving car is moving, at a good speed. It's operating its motor controllers. That's a whole other module. The car is moving. And then this subscriber that's looking at the camera data, processing it, and seeing the traffic light is red is going to say, hey, we need to stop the car. The traffic light is red, so we shouldn't cross this intersection. And when it detects that that's the case, it can send a request to a main server, which is all housed within the same computer that forms your robot's brain. And that server, I mean, it can be housed in other situations, but that would be a common implementation. But that abstracted server would communicate between this machine learning model and the motor controller and say, oh, the robot is seeing that we need to stop. So now I'm going to send a request to the motor controller to stop the robot, to stop the self-driving car, slow it down before it crosses the intersection to keep the passenger safe. And you would probably have responses to, just confirm message received or do something with that request, and then produce some new information. But that might be a need. But for sure, when an event occurs, you would want different packages within your robot to be able to request an action to be taken. And again, taking that from a wider scope, uh, that forms the foundation for this action communication model for ROS, where again, with a robot as opposed to a machine, you pre-program it, you hard code it to do the same thing, and it just runs through a hard coded set of operations. With a robot, you're asking it, hey, use your sensors and you come up with a plan to solve this problem that I need you to solve. And with the robot operating system, you can provide what's called services. You can have a goal-oriented task. You can say, hey, my self-driving car, I need you to take me from my apartment to my house and drive me to this restaurant on this GPS. And the robot will handle the rest of what's needed under the hood because it has this mixture of publishers and subscribers so it can manage data around its system. And it also has this client server architecture so that it can flag different events that are going on, request the different actions to be taken. And with that, you can have different modules put together. And the robot itself, once it receives that goal-oriented task of take me from point A to point B, it can come up with a plan for how to do that. It can interpret where it is in its environment, and it can start to move towards achieving that goal and providing some feedback, saying this is where we are along this planned path. So if you're not understanding everything that you're seeing in these diagrams, don't worry about it because we're going to get hands-on with them in the future, and you'll really understand them once you see them moving in action. But for now, just try to understand like this is what ROS does. It allows you to communicate between all of these different software modules in these ways that are particular to the needs of robotics. And as an example of that sort of action schema, the ROS navigation stack is something that's used specifically for navigation. So I was using self-driving cars as a big example throughout these past slides. And the self-driving car navigates from point A to point B. And ROS actually provides different stacked architectures where you can see a lot of these examples of nodes communicating with each other, servers sending different topics to different nodes. And really, this allows us to have a standardized system to handle a navigation task with the navigation stack. And there's other stacks for motion, for perception. Here's the navigation stack. And just by taking a quick look at it, you can see, let's just look at something very bare bones and very low level. You would have very specific formatting for how data is sent between different nodes, and you would have a standard way to name your nodes, like you would have local planner, global cost map. These would be aspects of the navigation stack that are shared among robots. So if you take two different robots, if you have a humanoid robot that's walking and it's walking around an environment, and you have a self-driving car that's driving around a road, um, if they both run this navigation stack and they're formatted in this manner, some things might change. Like the humanoid robot is using legs with motors to walk across its environment. So the motor control aspect of your robot would change. But how it actually gets around its environment, how it plans to move around its environment may be very similar to a self-driving car. Where a self-driving car, what changes is it's a car, it's driving with wheels. So that module for motion control may change, but this navigation stack won't. And by using the standard stack, you would enable different teams who are working on different robots to share software. So you can just take that software that works for another setting, for a self-driving car, for an industrial warehouse robot, and put it on this new robot, like a robot dog. And you can focus on changing what needs to be changed for that robot. You know, it's walking with legs instead of with wheels. And that would be something you would create, but you don't have to rewrite every other aspect of the robot from the ground up. So that's the real value add of the robot operating system. And you've noticed that we talk a lot about the robot operating system 2, version 2. And the difference between version 1 and version 2, among others, but kind of like the big concept that you would want to know about, is that ROS2 enables you to work on distributed systems. So we mentioned you might have a robot with a ground telemetry station, with a teleoperation station. You might have multi-robot systems. Um, ROS2 enables your nodes to be discovered across a network. So now it's not just the nodes that are running on your edge computer on board the robot inside of the robot's brain, but it can actually broadcast some of that information to your network and other devices on that network, such as other robots, such as other computer devices like a teleoperation station, like a ground telemetry station. They can pick up information from those nodes in a precise, in a consistent, in a reliable manner, and they can work together. And then you can enable these multi-robot systems, these multi-computer systems to do more interesting work. So when we've talked a lot about software on a high level, but we're going to dive a little deeper into what a ROS2 package looks like and what the ROS2 architecture on your computer would look like. If you don't understand everything you're seeing right now, I wouldn't worry because you're going to immediately see this live on our simulator. But just this is like more of a high level overview of what to expect and to understand what you're looking at within a ROS system and how it's different from others. So a ROS2 package, where you would host the code that you're writing so that you can accomplish a goal, that you can accomplish a task using your robot, would be made up of several different components. And this is becoming important not just so you can navigate creating these packages yourself and developing code for your robots, but also if you were to grab code from another developer from another organization that's providing a package to accomplish some sort of goal on your robot, you can understand how to navigate their package and understand what's going on. So the package XML file within your standard ROS2 package contains licenses, metadata, dependencies, the authors that created that package, the setup.python file. .py is the extension for Python. You would run it and it would contain the instructions for actually using that package and establishing it in your robot current environment. You would have a .cfg file that helps ROS2 find any executables needed because you're not necessarily going to give ROS the exact directory to find all of these different software scripts that you're going to implement. You're just going to tell ROS, hey, ROS, please run this package, this particular package. And within the ROS2 workspace, it's going to try to find that package. And it's going to use this CFG file and the resources slash ROS2 package folder directory in order to locate among other packages that you have, okay, this is the one that you want to use. And that way it can use what's inside of it. Other contents within your package that you may add but aren't completely necessary are those nodes. You might have publishers or subscribers. You could create those in C++ and Python and other languages. You would have launch files that would start up those nodes and have their initial parameters. You would have configuration files if you need to switch between different parameters for those nodes or otherwise change different environmental variables. You would have dependencies. So if you've developed software before, you know that you may install external libraries or other packages. For example, with that vision system, you may be using OpenCV, CUDA, other systems. And you would have to identify what those dependencies are, identify which versions of those packages you're using. And that way your system can use the most appropriate package for the software that you developed so that not much changes. You would also you should have documentation inside that shows you how to use that package, instructions for implementing it, descriptions for what it does. And finally, you might have testing, especially if you're working on production systems. You'd want to have unit tests, integration tests, other forms of tests to make sure that when you write some new software for your robot, it actually works seamlessly with the other systems on your robot, and it also, um, you know, does what's expected, doesn't create some kind of bug around your system. That way, you can feel safe deploying that software on your robot. When it comes to those communication architectures we spoke about before, the publisher subscriber, the client server, the action, Uh, these are going to be housed within different ROS2 files, the .message file for sharing data among nodes that would look more like a publisher sharing data to different subscribers. You would have SRV files for services. So if you have that client server type, request something and then get a response type communication, that would be under these files. And then for the action, for that goal-oriented decision making, you would have a .action file. And all of this is going to be housed within what's called a workspace. So ROS2 has um, a methodology so that you can house everything under a sandbox. You can work on your software within the sandbox of a workspace. You can try things out. You can then switch between these different sandboxes. So if you have a workspace here, you're trying to develop an algorithm in one way, and then you have a workspace over here where you're trying to develop the algorithm in a different way and you want to test them both. You can switch between these multiple different workspaces, the different sandboxes, all on the same system. And when you install ROS2, it'll create a workspace for you by default, but you can always create more. And when you create more, always there will be an active workspace and there will be a command that we run on the terminal to initialize a workspace as our active workspace, and you'll see what that is. But whatever your active workspace is what will take priority when you're running software. So again, if you have a workspace here, it's running one example of an algorithm, one idea that you're trying to run for an algorithm, and you have another workspace that's trying to implement the same sort of goal, but it has a different algorithm to accomplish that. Whichever one of those workspaces is active for you at the time is going to be the one that takes precedence when running that software. So you can feel safe when you tell the robot, hey, run this action, it's going to use the code that's in its active workspace. And finally, a feature of ROS, which we're not going to touch on too much, but just so you know it's out there, is that you can overlay different workspaces. So you can put a workspace inside of a workspace, and the workspace on the highest level in that pecking order will be the one that has priority to run. A workspace looks kind of like this in this format in your directory. You would have your ROS2 workspace folder with the name of the workspace, and then inside it, there would be a few consistent directories, a few consistent folders that you'll find. Usually when you're first starting out your workspace, all you're going to have is that SRC source files. That's going to be all the software that you develop, and that may include a lot of different aspects that we talked about before in the packages, because your packages are housed within those source files. They're in that source folder, and your multiple packages that you create for your workspace are all going to be housed there. And when you download or copy over someone else's ROS instance, if you have an image of ROS from Docker, if you're grabbing code that someone else wrote from GitHub to use on your robot, and they had a workspace that they're sharing, they're going to have all of their source code inside of this SRC folder so you can see it. Now, when you build, and building will be a command that we run on a terminal, it'll actually take that source code and form a full workspace around it so you can set up your workspace and get it active running on your system. Then you'll create a few other files alongside that build action. You'll have a build folder that creates some artifacts for different operations that were completed during the build process. So you're probably not going to interact with that build folder too much, but it may be important if you're troubleshooting something that went wrong. You'll have an install folder that has all of the resources that are needed to install packages that you're using for your robot. And your setup.bash file will be in there, which will become an important file that we run a lot to establish our ROS2 environmental variables and activate our workspace. So that'll be the file that we use to make sure this is the workspace that is active at the time. You'll also have logs. So again, for the process of troubleshooting, for seeing what went on in your robot, that'll be pretty useful folder. It's probably not going to be used nearly as much as your source folder as a developer, but definitely it will see some use as you're going through the process of understanding how to make improvements, how to make tweaks to your robot. You're going to check the logs. And finally, you'll have a CMake list text file. And if you're coming from a background of programming in C++, CMake may be more familiar to you for setting up your dependencies. But for those of you who are not familiar with it, um, once again, we need to manage dependencies. You have different versions of software. I might be using Python 3.7 or 3.11. I might be using OpenCV, one version or another. OpenCV 4, OpenCV, there's just all these different versions. And um, we need to, as developers, make sure that we're using our dependencies under versions that work together with each other, because a new version of Python might come out and maybe other open source software that we're using, like OpenCV, hasn't caught up to some of the features that are coming out in that new version of Python. And so if we're just using the most recent version of everything, we might write code that works today, and a week from now it doesn't work. And nothing changed about the code. It's just if we're just using the most new version of all the dependencies, then we don't have any guarantees that they're going to work together for the future. But with the CMake list text file, we can establish these are our dependencies, and these are the versions of each that we're going to use. So that's, yeah, in the future, if someone takes our image of ROS2 and uses it on their robot, they'll use the exact same dependencies that we were using, and our code therefore should be the same and work the same on their system. Now, that's really all there is to know about ROS on a high level. We're going to get more into the weeds in the next few videos in this tutorial series. I do want to be clear that a lot of the contents in this tutorial series are coming from this reference book. It was recently published at the time of making this video. It's on Ava. It's a technical writing sharing marketplace. This book, Ultimate Robotics Programming with ROS2 and Python, is going to be extremely beneficial if you would like to purchase it. It's pretty inexpensive. It's just $20. That's what I paid for. It's to get a digital PDF copy. And with this book, you don't need to buy it in order to follow this tutorial series, but it will make your life easier because there's some of the content in this book that I'm not covering. I'm not going as into the weeds as the book does. So if you really want to understand what you're working on, I recommend getting this book. And also with the book, we're going to be running different commands, different code. You can follow along to some aspects, for the most part, just by following along with what I'm doing. But it will make your life easier if you can access that same GitHub repo where a lot of the code will be housed. And if you can also see the reference code that's in the book, I'm going to be going back and forth between the PDF copy and the future videos in this tutorial series, and copying and pasting some code into the terminal, or copying and pasting some code into a particular file. And while you can just rewrite the code that you're seeing on the screen, it will make your life easier if you can just access that reference code that's in the book in the GitHub repo of the author. So please consider buying the book. I'm not getting any benefit from telling you that. I'm not an affiliate. It's nothing like that. It's just a pretty inexpensive book that's really good on robotics programming, and you'll get access to more seamlessly be able to follow this tutorial series if you have the book. And now let's talk about actually using ROS2 on your systems. So we talked about how that book has some components that I'm not going to cover. I mentioned that usually with these workshops, you would have to run through a lot of installations to use ROS2. You would have to install a virtual machine or dual boot a computer, install Linux, change your permissions in Linux so you can install the appropriate dependencies and then install ROS2. Rather than going through all that, if you want to learn how to do that, the book has some great information on how to install ROS2, and with the code that you would run, with how you would navigate your terminal. However, we don't need to do any of that to start to implement some of the features of ROS2. I just want this to be as easy as possible for you. So I'm going to introduce you to a great service called The Construct. They're an organization that provides tutorials for programming robots, understanding robot theory, using ROS. And within that, they have a web simulator where you can simulate a Linux distribution computer running ROS. And we're going to simulate a computer using Humble. So once again, you don't need to install anything, you just need to create an account. And I'm going to show you how to do that in a moment. So here is the construct. I briefly paused to switch over and log into my account. If you just go to the construct.ai or look up the construct on Google, you'll find this website. You'll see this logo. That's how you know you're in the right place. You would have to create an account. If you have a Google account or something, you can just log in with that. That's the way I do it. But there's, you can always create an account by your methodology, create a password. It's just kind of like the same process as usual. And by doing that, you'll get access to this website where I'm on the homepage. So this would probably be the first thing you see. Yours might not be populated with different courses or your projects if you're just starting from a fresh new account. But with this program, and again, I'm not an affiliate of them, you can create an account for free. You can go through a lot of their content for free. I actually have the free account right now. I'm not paying anything to use this. So it should be exactly the same for you here. With this, before we get into how to use ROS2 on here, um, you can actually go through different courses. So we talked about how you would want to know some basic Python, Linux, C++ would be beneficial, and maybe understanding some other aspects of robotics. There's a lot of different courses. Maybe that would be beneficial for you. Unit testing, some of the things we talked about that you would see in a robot, you would see artificial intelligence, you would see the manipulation stack, the perception stack, the navigation stack. We talked about that in those previous slides. If you wanted to learn them, this is a great resource because it's on a web simulator, so you're getting hands-on with them directly. Um, and these three courses, if you're brand new to robotics and you're starting to learn this from the ground up, you can go through them. You can step away from this tutorial series if you want to start from the ground up, and this would be pretty beneficial for you to understand what's going on. But picking up Python 3 for robotics, C++ for robotics, Linux for robotics, these three courses are free, so you don't need to pay anything. And if you want to go deeper into robotics, then there's a $40 subscription for accessing these other courses. Again, I'm not getting any benefit from saying that to you in terms of, they're not paying me. I'm not some affiliate. You're, this is totally up to your discretion if this is something that you want to follow. I'm naturally going to be putting out some tutorial series for some things that aren't included necessarily in these courses. You're going to see some things in this tutorial series that this video is part of that aren't included in these courses. But this is a great starting point to learn a lot of the different things that you can do with ROS2 and how to program different modules within your robot. And I really recommend it. But one of the neat things about the construct isn't just that you're going through these courses. You can actually go to this develop section. You go to my ROSjects, which is your projects. And again, rather than going through the full installation process of ROS2, rather than going through, creating a virtual machine, creating a dual boot, installing the right version of Linux, installing the dependencies, setting your permissions correctly in Linux, and then installing ROS2 and vetting whether that works, you can have a working version of ROS on this web simulator to the performance of a pretty good embedded computer just by going to this develop section, clicking create a new ROSject, and then it'll ask you which ROS distribution do you want to use. So we're going to be using Humble. It's going to ask you, which sort of simulator you want to use. So this is pretty cool. You can see all sorts of simulators that would be pre-populated for you. So if you want to if you want to use a particular robot model, they have a ton of different robot models. If you want to use a particular setting, so you want your robot to navigate a kitchen or navigate a maze or navigate, the Stonehenge, you can just pre-populate your simulator with that and start to get working with it. We're going to put, I will create mine, but just something to know. And then you just create a title. It's that easy. I'm going to call this ROS2 tutorial series. Great. And with that, um, it's going to create the simulator that we can run. You can always download all of your code that you write in here. And when we click run, we're going to enter what's called the ROS Developer Studio, which you'll see it loading here. And this is going to allow us to use some of those tools that we mentioned in the slides before. Like I'm just going to briefly open that PowerPoint so you can see. We mentioned you might use Visual Studio Code, you might use Linux in robotics. Here in this, let me close this out. Here in this web simulator, you have a version of Visual Studio Code running. So if you've used Visual Studio Code before, this interface may be familiar to you. If not, don't worry, we're going to be navigating around it during the tutorial series anyways, so you'll kind of get the gist of what you need to do and you can follow along. And you'll see some of that folder structure that we talked about earlier. Here's your ROS2 workspace. It's the default installed workspace that we mentioned before. And then you have your source folder, which I created a brand new instance of ROS2 Humble, so there's nothing in there. But you also have your logs, you have your builds, install, these different um, folders within that workspace structure. And throughout the course of the next tutorial in this video series, we're going to start to create a publisher subscriber, create a package that goes into our source folder and start working on our own source code so you can understand ROS in a hands-on way. But one of the cool things about the simulator is that it's not just the IDE. You can access the web shell, you can access a terminal and run different terminal commands. So if you're familiar with Linux, you might know how to navigate a terminal. If not, you can follow along with us and run some of those commands. And if you go back and learn Linux on your own, whether you're using the construct or another tutorial series, you can get to understand Linux and do more with this. But for now, you can just follow along. We could see which files are in our current directory. We want to use that ROS2 workspace. We can go into that ROS2 workspace and see what's inside of there. There's our build, install, log, and source. We can run different commands. We can run our source code. We can run that setup bash file to set up our workspace as the active workspace. That's all going to happen inside of this terminal. And that would be the same way it runs on a Linux computer. So if you were to dual boot your computer, if you had an edge device like a Raspberry Pi or a Jetson Nano and you installed ROS on there so you can control a real robot, this would be the exact same procedure. You would open up your terminal and run some commands. And you have your code editor. If you're developing in code for in Python and you want to, it's not necessarily touching your robot yet, or you're developing a machine learning model, you have Jupyter notebooks directly installed on here that you can open up and use. And messages. Here you have a lot of the different tools that you can use in ROS already installed for you, already configured to work seamlessly with your project. So for example, we can open up Gazebo. It's loading. And we have no robot running, but just it's as simple as open up Gazebo and set our simulation to run, and you'll see that more in the future. So we can start to run some of these cool simulations that you saw earlier on Gazebo. And, once we have our robot built in, we can do that. You'll have different graphical tools like RViz, Guacamole. You'll have different visualization tools to see what your sensors are saying, see where your robot is in 3D space. That'll be in this little section called graphical tools. You can review your course notebooks. So if you want a reference for how to achieve something in ROS and you want to look at either some documentation or look at how you achieve things in some of the previous courses offered by the construct, like that's C++ for robotics course that we saw earlier is in here. If you want to review how to run commands on Linux or some Python 3 for robotics, you can kind of click on these tabs and go through some of the units that they provide in the training offered by the construct. So you can use that as a reference when you're programming your robot. You can look back and forth, cross-reference, and see this is what I want to accomplish. This is the command I want to run on the terminal. This is the Python 3 type script that I want to write. You can access that immediately in your workspace. You can connect to many different robots. We'd have to add the robots in, so they're not available yet, but we can do that. There's an OpenAI instance here that we can use to get some coding assistance. And there's always this Go Home tab that we can just click on to go right back home. Check other projects, go to our profile. So this is a pretty nice resource to learn ROS because you don't need to install all this stuff. It wouldn't just be installing ROS if we were going from the ground up on an edge computer or on a virtual machine version of Linux on a dual boot. We would also have to install a lot of this other stuff. We would have to install Gazebo. We would have to install Jupyter Notebooks. We'd have to install Visual Studio Code, our IDE that we're working in, if you wanted to work on something like that directly. So we're skipping all of those installations, and you can just create an account and open this up and work on it directly. And this runs pretty great. I mean, you can get more processing power out of running it on a real system, but this runs about as well as a pretty good embedded computer for hobbyist use. Like, I don't know if this information is up to date, but in the past I've seen that you can change if you have the paid version how much performance you're getting, but for the free version you're still getting about the performance of a Raspberry Pi 4, which is a pretty common hobby embedded computer, and probably a computer that you'd be using early on to play some of your systems. Once again, if you want to go through the actual process of installing all this stuff, it would benefit you to learn that if you really want to work as a robotics developer. But for the sake of this tutorial series, once again, we're not going to focus on all of the nitty-gritty. We're just going to get you started programming in ROS2. And one last thing to know about the simulator, you'll see this timer running. I have it at 6 hours and 58 minutes. Every day for the free version, every single day, you're allocated 8 hours where you can run the simulator and play around with different aspects of it. When you run out of those 8 hours, which I don't think you're going to spend 8 hours here a day, but if you are, kudos to you. Then it'll restart the next day and you can continue to work on it. Naturally, that's one of the drawbacks of doing it on the simulator as opposed to on a real system. But again, we're skipping that installation process, so you can just get started right away. That brings us to the end of this particular tutorial video. I just want to show you the GitHub of coming from that book that we're referencing, and as well the book itself. Here's my PDF copy. You naturally can't access this link because it's native to my computer. But if you buy the book, you can get another Kindle copy, a PDF copy that you can view over the internet. You can go through some of these chapters. Not going to show too much of it. So, if you want to get the book, you can. But just as an example, here's, the process of installing ROS that I didn't cover. I'm not going to view all of it because you should support the author. And then also, these are some of the commands that you can just copy and paste and run directly on your terminal to check different things that you would want to be using, not just for the installation, but for some of the future tasks that we're going to be doing. So once again, you can just follow along by watching the video. If you want to write out some of the code yourself, you can do that. But that would, please support the author and get the book. That would be beneficial for you, and it's pretty inexpensive. So I will see you in the next tutorial video. We're going to get started with using Python and ROS2 to create some nodes, create a publisher subscriber, and we'll talk more about it in that video, but we're going to show some cool things that we can start to do in that simulator. I'll see you then.